And we are live for our chiller questions answered. So, officially, this is going to be the series moving forward. We've been doing some live streams for a couple of months now, I guess, or something like that, several weeks. But given just communicating with everybody, uh, it's been made clear that we should just go in a more general, open direction than trying to get too topic specific. Now, it is useful in having a specific topic of some sort, but having a more open and general approach has very much been voted in favor of. So we're going to just move forward with that format. And everybody wanted to refer to this as the Chiller Questions Answered series, which, hey, I think is a fine name. I am perfectly happy with it. I am not complaining. And I'm not going to make the mistake I made last week and push the wrong button. So let's not do that again. I've already configured that here. So I do want to throw out there that next week is going to be a fun one because it is going to be kind of our anniversary stream. So it will make 1 year, one full year of being full time into the academy. And I'm very excited about that. I actually plan to kind of pull some of the numbers together and share some of that kind of behind the scenes of how many people we've had join the academy, what some of the uh, I guess results of that were. I'm really excited, just kind of watching things as they've gone over the last year. It's been just exhilarating. I really love this whole process. Really excited about what we're doing and getting to continue this going forward. Now, if you are a YouTube viewer only and you haven't gotten engaged in the Academy, I just launched this series and I have an internal portal now that all this is going to flow through inside of the Chiller Academy. So if you would like to access that portal, be a part of that, go check that out over at chilleracademy.com. You can get into the portal. You can get your questions in there ahead of time. So the way that this stream structure is going to work is I'm actually going to prioritize the early questions that came through in the academy segments and make sure I get those covered first, and then we will get into any questions in the chat as well as which if you have those I'm going to start at the top and just kind of work my way down. So feel free to go ahead and start getting your questions in, and I am logging questions as I go forward now. So if you have questions that come up or you want to know something, feel free to go ahead and just post those questions, whether it be in a comment section or ideally, if you really want them answered, go post them in the portal at the Academy. And I'm going to start trying to track these and make sure I keep a log of questions that we need to answer that are floating around out there. Because one of the things that I've started to really root and get more familiar with is you're not the only one that with that question. And one of the directions I'm trying to go is I really want to put more focus on addressing what you're needing and what your needs are, and less about what I feel like necessarily making something about, which is what I've done. I think it's what most of us do is we approach it from a state of we want to talk about this, we want to do this, and we feel that this is something we feel comfortable talking about. That's the other side of it is sometimes it's just our own comfort level that we're trying to have a conversation around, and it doesn't always put things in a position where you actually get what you want to know answered appropriately. So one of the things I want to do with this new approach to how I'm doing this is I want to actually just make the whole, say, content cycle that I'm making focus completely around what your questions are. Because if you have that question, dozens, if not hundreds, if not thousands of others have that exact same question. And if that many people have that question and they're not finding a reasonable response, this is a way we can start to get some of those out there more efficiently. So that, just to kind of share some of the thoughts I've had around this. And welcome to the stream, everybody. I see you jumping in here. How you doing, Jason? Good to see you, bud. And oh, so the ask an off topic. Well, sent working and close. Yeah. So there is no off topic here. Okay. So going forward, I know we've done kind of a topic based stream, but going forward, there's not going to be a overall topic like there has been. I really want to make this. You have a question, you jump in, you ask it. It doesn't. There's no limitations on what the questions are that we're going to try to pursue. Okay. So with that, I've got quite a few stacked up. Let's get rolling into the questions. Again, feel free to jump into the comments, post your questions you have, whatever you've got, and we'll keep it rolling as best I can. Really appreciate everybody's time. Let's go have some fun. So, first question up. Closed loop chiller flush, best practices. So, we've got a closed loop. We want to flush the loop out for whatever reason. So there's two kind of lines of thought that comes to mind with this. One is, let's say we want to do some kind of strainer flush, or we want to maybe there's a low spot in the loop somewhere, okay, and we want to flush out that low spot for some reason. Maybe we've got like in some loops I've seen it to where there'll be certain areas that kind of collect sediment more so than other areas, just because of how it kind of makes a trap where it's at, right? And it's somewhat due to poor piping. Usually, it's been my experience. Either way, you want to do a flush. One of the things I will say with closed loop, we want to be very, very careful with flushing, how much we flush, and when we do so, specifically because of the chemical treatment in there. It is very important that our closed loops be chemically treated, and that they've got what do they call them? Is it deionizing or deironizing? I'm not a chemist in the chemical treatment side of things. The point is, there's certain additives that they put in the loop, and that's one reason why it looks pink sometimes, or at least most of the loops in my area, that's the color they would turn. Is because you have those additives in there are preventing things like rust on the internals of the pipes. That's one of the things that'll happen. So we want to be very careful when we're doing any kind of flushing, or if we're opening up a closed loop, that either the facility we're working at is aware, or their chemical team, or if we're working directly with a chemical company, because I've done that too in the field, where we actually brought the chemical with us, or a chemical company in and we manage them directly as part of our contract with that facility. The facility themselves did not manage chemical treatment. However it is that you're set up, you want to make sure that that team is involved, because whatever water you take out, that's going to cause fluctuations in that chemical treatment, which, if you're not careful, can have severe side effects with erosion on the piping, and that'll also have a huge impact on that water's ability to actually transfer heat and such, has been my experience. And I'll get into a story on that in a second. So, yes, with flushing, if you're going to do a flush, if you're flushing a strainer, so I'm not a huge fan of flushing strainers. I know it's a known, or let's call it common to some people, practice. I personally have found that if a strainer I will open the drain port on the strainer, or the flush port, to check to see how much comes out, and that'll kind of give me an indication on how bad the strainer may be. But I personally have not seen where, say, flushing a strainer is an effective way of routine maintenance. If it needs to be cleaned, it needs to be pulled and cleaned, is my personal opinion. That's also just given the context of the plants that I've worked in and the type of debris that I deal with. That may be different in other areas who have different climates. I don't know. I only know my region, that it wasn't the most effective thing. We get a lot of leaves, we get a lot of heavy sediment and mud. So because of that, I'm not a fan of flushing a strainer. Okay. Now, if you have to flush, just be very cognizant of, or mindful of, the of the amount. You're trying to minimize it as much as possible. And I like to flush from the top down if I'm going to do a loop flush. So let's scale into that. I've had scenarios where we had a closed loop. The loop was not treated, was not taken care of, and in one particular case, it had completely filled with basically iron, right? It looked like rust, like the water looked like liquid rust. It was so dense, and it was because because of the lack of treatment, it had ionized and was full of basically iron particles and the rust particle from the way I understand it. And it was heavily impacting that chiller's ability to exchange heat correctly, which we were actually, how we found this was we were getting ready to change this chiller and we started opening some stuff up and we found the condition of the water. It's like, holy cow. So in a scenario like that, we drained the loop. We started at the top, opened up some air valves, let the whole loop drain out because we wanted to start with fresh water and we also wanted to get chemical treatment in that water this time as well. So that's exactly what that process looked like, just a complete top to bottom drain. We didn't do any flushing or anything. We could have. So if I was to have actually flushed that loop from there, what I might have, there's a couple of ways that I personally would have thought to approach it. One, we could open the bypass on the makeup assembly and let it flush and drain down that way. Now, most of the time, your makeup is going to be on the return or the suction side of your pump piping. So it's going to be pulling back. So if you just open the bypass on your makeup water assembly, then that's just going to put water basically down that one pipe, path of least resistance. So I would end up, I'd probably flush that side of it for a little bit and then close a valve somewhere to allow that water to then pressurize back into the supply side that would technically be coming out of the chiller, going back to the air handlers. And I would flush down that way. That'd be one way. The way I would probably go about it though is I would probably pressurize the loop. So drain it down like I discussed, pressurize it, maybe even get it circulating for a few minutes and let that water flow and pick up as much sediment and debris, whatever is in there, as I can. And then open that valve back up and let it flush back out. And it would be another top to bottom flush. So to do a clean flush like that, you have to open ports up at the top of the loop. That way air can properly come in and things can flow in a downward direction and then draining it down at the bottom. Now, that's going to depend on, you've got to figure out your drainage situation, whether that's, to ground or to a drain or whatever that looks like. And depending on your chemical treatment, so be careful of this, depending on what is in your loop, you may have regulations in your area where you can't just drain to a drain or something, right? Or at least not that much quantity. So that's a pretty severe one, right? You're talking about a whole loop flush, which unless you've got a scenario like I described where the whole loop is severely ionized, that only had that happen that one time. Now I've had some really dirty loops, and when you're doing a commissioning startup on a closed loop, you're going to have a lot of construction debris. That's where your strainers come in, and you can actually put startup strainers and such in on some of these, and even some of them actually come with it. Where the new install, they'll actually have a temporary strainer that's on the strainer itself, that basically you'll use that during the first little bit of startup. That may be the first month, first 2 months, whatever it is. You'll have that startup strainer, which will be a finer mesh that'll collect a lot of the just general construction debris, and then you can remove that, use a regular strainer from there, because that startup strainer is just too fine for normal operation without having to clean that strainer all the time. So that would be like using strainers to capture a lot of the sediment or debris, whatever it is, would be a more common way to go about it without having to flush the loop. So anyway, in terms of flushing, be very mindful of your chemical treatment. Don't throw that out of whack. And if you always have your chemical company involved in that process, please. And then if you do have to do an actual flush, like then I'm going to say we've probably got a pretty severe scenario. There's some of these cases where they can put some chemical treatment in there and it will actually stabilize that water in a way to where you don't have to do a flush. That's my understanding, at least, talking to some of these guys, where there are certain things they can do that'll help, say, allow a lot of that heavy sediment that may get in the water to settle because of the chemical additives they put in, stuff like that. So yeah, hopefully that is a useful answer. Hopefully. Okay, let's do this one here. Give me 1 second, get it loaded up. Hope y'all are having a great start to your week. Appreciate everybody joining the stream. So I've got a couple of questions on reserve I'm going to hit real fast. That's what I'm working on now, and then I will start working through some of the questions in the comments. Okay. For drive assemblies, can we go over general alarms like overcurrent, DC bus issues, etc., and what each alarm might indicate? For example, DC bus issues could mean bad bleed resistors. Yes, absolutely. So an overcurrent, let's start with that one, because there's a whole bunch of directions we could go here, but let's focus on just a couple you mentioned here. So with overcurrent could be an indicator of a lot of things. All right, we could have a brownout or a voltage drop scenario from the grid that could cause some kind of overcurrent issue if it was a sudden drop, which was going to cause our current to spike. We could have a megging issue. Maybe the stator insulation is beginning to break down and having trouble. So that could be causing a leakage to ground, which would eventually show up as a potential overcurrent if it got severe enough, right? Or some drive assemblies are smart enough now that they'll actually just detect, hey, we've got a earth ground scenario here. I'm not going to turn on so that basically the drive is essentially megging the motor, if you will, and it sees that it has a path to earth or ground before it even outputs to the motor. So at that point, hey, I'm not going to blow myself up intentionally here. Something like that. So that could be another overcurrent condition. Your load itself could be an overcurrent. So there's going to be some cases where, especially if you're in a pull down scenario, so this will be something to be mindful of, is during a pull down, you're way above set point. You've got a lot of heat in your loop and you're trying to pull that down. Well, the chiller itself, if it doesn't have a built-in pull down programming, or even if it does, they're not always programmed. You want to be cautious to have that chiller fly to full peak and try to pull that down, because what'll happen is it can push up against the current limit safeties. And because there's so much load the chiller's running at absolute maximum to try to process that down, it actually has a lot of, call it instability, and it can have these spikes, and those spikes can be enough to push you over a current trip, and you'll trip on overcurrent, even though all that went wrong was that you had a really high load and it was trying to pull it down. So in a scenario like that, if you're coming up to a loop that has a hot pull down that needs to happen, and it doesn't have a built-in pull down cycle, just a quick and easy lower the current limit, let that pull down, get close, even within just a few degrees of set point, right? If you can just get it to where the chiller is coming into set point and things are starting to settle out, it's going to take longer, technically, to get there, because you're not letting it go to absolute maximum. But even just a current limit of 80-90% is still better than, say, leaving it at 100%, where it's going to start pushing that upper safety limit. So if you could do that might prevent a overcurrent issue. Let's see. With a centrifugal, an overcurrent could be the IGVs at startup are open too much. Now, the Danfoss turbo core specifically does open the IGVs prior to start. That's a different scenario. But most centrifugals want the IGVs to fully close, the inlet guide vanes, to fully close to help keep motor current down at startup. And there are some cases where they will trip out on overcurrent if those aren't closing properly. And you'll never be able to get past that startup phase to get the motor online. Let's see. I'm trying to think of other overcurrent scenarios. Yeah, there's a lot of so there could be something with the drive assembly, right? So if there's a drive assembly issue, that could trigger an overcurrent condition. A surge can trigger an overcurrent condition because of the heavy fluctuations that it causes. Now that's back into centrifugal land. If you're dealing with a screw and you're going into overcurrent, you may be having a unloading issue. Now this would be saying you have a slide valve specifically, so variable speed. This wouldn't necessarily be the case, but with a slide valve, those can stick and they won't always slide smoothly and allow that compressor to unload, which basically limits how much of the screw bolts are actually compressing at a given time. So if that slide begins to stick, it can get stuck in a loaded state. Heck, I've also had it to where somebody miswired in the panel, just genuine mistake or otherwise, and they wired the one of the solenoid coils for loading straight to the output source. So it was just constantly getting voltage to load up, and they just stayed there. And so it severely struggled every time it tried to turn on because it was just going straight to full load amps and then tripping off. Not supposed to do that, right? So it could be something as simple as that that's causing an alarm issue. And we do have some screws now that are on drives. By drive, I'm assuming you probably mean variable speed drive, even though a drive package could be a number of things, such as soft starters and such. But we do have some screws that are coming out with both. They'll have a slide and a variable speed, and so they'll use those in conjunction in different ways. Daikin has their way of doing it, Dunham Bush has theirs, but the same kind of theory can still hold true to a degree, where if that slide is having trouble, then even though it's on a drive, it could be causing a current issue because that slide may not be unloading the way that the chiller wants it to. Now, if we move into DC bus, yes. So if we're holding voltage on the bus, then the bleed resistors are likely not working. And because they're not working to drain the bus down, that will trigger a DC bus fault of some kind, or DC voltage fault, just kind of depending on your manufacturer, where the drive has de-energized, but the DC bus is not draining, and that has to happen within a certain period of time. Otherwise, it sees that as a fault condition. Now, you could also still have a DC undervolt, DC overvolt condition. Those are probably going to be something either with the capacitor bank or the SCRs or IGBTs, depending on the style of drive. So that's something to note, is our rectifiers that we're using nowadays. We used SCRs, silicon controlled rectifiers, for a lot of years. And we're seeing a transition, especially I would say with York, where they're no longer using an SCR, they're using an IGBT, insulated gate bipolar transistor. So now we're using IGBTs to not only rectify coming into the DC bus, but then we're also using another set of IGBTs to output a PWM to the motor for variable frequency. So either way, that rectification device, whatever that is, could be causing an issue, and we're seeing that in our DC bus having sudden spikes or load dips for some reason. So that could be the thing. Part of my point, this is a pretty broad question, and it's not a bad thing. But when we start talking these drive assemblies, there are an abundance of conditions, and this is, we start say we just kept it as simple as a XL or a a wide delta starter. Those are probably some of these are the simplest forms of a drive package we have. There's quite a lot of various conditions that can cause a lot of different alarms. Now, um, the as we scale that into variable speed applications, that just becomes infinitely more of trouble because we've got a lot more control boards, a lot more electronics. There's a lot more happening in that electrical circuit. So just, yeah, a lot can go wrong with a drive. But hopefully that gives you something more to kind of go off of, specifically hitting on your overcurrent or DC bus issues. And that gives you some kind of direction to go with of some kind. I do see wouldn't snubbers help bleed down the caps? Not in my experience, no. Snubbers are kind of a just like the capacitor bank itself on the drive assembly is a type of filter. And when I say it's doing a couple of jobs. One, it is filtering the DC bus, helping give a cleaner, more pure DC. It's not pure, but a more pure to the inverters. Okay, so you're leaving IGBTs, those are your inverters. So they are filtering in that way. They're also holding a bank of power to give a more, as part of the filtering process, but to give a more even distribution. And then we can use that power bank that's stored in the capacitors to help us during the coast down cycle with some of these compressors so that, like with the mag bearing, we can gently ease down, something along those lines, instead of just hard stopping. So the capacitors are being used in that function. Now I scale that to the snubber side. So if you don't know, a snubber is they're these little capacitor blocks that are sitting on the inlet side of the inverter, coming in from the DC bus into the inverter, and then leaving that would be the motor. And they sit across the positive and negative terminal of that inverter, and basically they are a type of they're a filter. They're helping continue to clean that current as it comes into the inverter. But I personally have not seen where the snubbers have done anything to affect the actual bleed down process of the capacitors. They have strictly served as just a filtering, and that's where the snubbers themselves are not technically a load. So like the capacitors, because the snubber is a capacitor, by the way, like most of them I see are like a 1 microfarad capacitor, but they're being used as filtering. And so just like the capacitor bank that we need to drain down are capacitors, well, those are capacitors too, and they're just going to kind of store and hold a charge. So they don't have a load function like a resistor does, where a resistor will connect two sides of the circuit and bleed through the resistance to drain that power down via an actual load. So I see RC snubber equals resistor and capacitor. Maybe that's true. I'm not familiar with that. The lip seal. So yeah, the snubbers I'm used to seeing on a routine basis. They're I don't know of them having a resistance based feature. They are just strictly they're a little mini capacitor for filtering. That is their primary function. And then we have the actual bleed resistors that serve the function of bleeding down the drive assembly. Good question. So it's good input. I like I said, I'm not familiar with the snubbers being used in a resistance type of function beyond just a little mini capacitor for filtering. Okay, let's get to the next question here. All right, I will do this one, and then we'll jump into some of our comments questions here. So these questions I'm hitting right now are from the portal inside of Chiller Academy for this live stream. So if you want to make sure you're at the top of the list and get your questions in, feel free to join that portal. I'm going to cover this one, and then we're going to do some chat questions as well. Okay. I am a graduate from the Ferris State University HVACR programs. I remember my instructor, John Tomziak, I struggle with that name, I'm sorry, talked about high compression ratios, a symptom of high head pressure. High head pressure will lead to lower volumetric efficiency. My question is, surging and high compression ratio the same thing with centrifugals? So one of the ways I want to phrase this, to answer directly, is surging and high compression ratio the same thing? No. No, they're not directly the same thing. So with a centrifugal, we refer to it as lift, and lift is just what I would consider a simplified version of compression ratio. Okay, so with compression ratio, we take our discharge pressure, condenser pressure, evap pressure, suction. So take those pressures, bring them to their absolutes, which is adding 14.7 for at least as a generic sense. Your elevation matters there. Anyway, get them to atmospheric pressure, and then divide them into one another. That gives you your ratios. And so, like the turbo core operates off of compression ratio instead of using an actual lift value, but most chillers we're using lift, and I prefer saturated lift. So instead of looking at the actual pressures difference for your lift, I like taking the saturation values, and it's just a basic subtraction. And so it's doing a very similar thing, but we're doing it in a simplified way, which I prefer because I'm just not that good at math, and I can quickly think about lift in ways that compression ratio, I got to kind of turn the gears a little bit on. Anyway, that is what we're using with a centrifugal is lift. Now, in terms of high head pressure, so high head pressure is the most common way that we can probably struggle with lift conditions. We usually struggle with high head, high condenser water in a centrifugal application. And so it is not the only thing though. So with a centrifugal, our load and operating conditions have a huge part to play because of our tangential and radial velocities, which impacts what our velocity vector is coming out of the impeller. Those have huge impacts, and depending on where that is, which is basically just what is the path of how much energy and what is its path of the refrigerant leaving the impeller going into the diffuser. That has an impact on where we are and how we respond to different stages of lift. So the more flow and the more velocity we can maintain on that refrigerant, the higher the lift capacity we can have. So in one scenario, we can have a really high lift, but because we have enough load to have a high flow, and we can really put a lot of velocity into that refrigerant going through the impeller, then we can maintain that high lift with no issue. And you can run what would be considered normally like crazy high lifts, but the chiller's cruising along just fine. Well, that's because we have the load to support that, and that chiller can really open up and breathe and let itself run. But as the load begins to reduce, and the chiller, to maintain leaving water set point specifically, the chiller has to cycle down without overshooting. Well, then we're not adding as much velocity to that refrigerant because we don't have as much kinetic energy added, aka velocity. Then the amount of lift we can manage also gets reduced with it. So that's where that surge curve ratio comes into play. So with a sorry, I'm seeing the chat here. With high head pressure, yes, we will see higher ratios or higher lifts. You can use the term ratio or compression ratio and lift almost synonymously in a lot of scenarios. or use them as the same thing. You're not saying two different things technically. But surging itself is not just a direct compression ratio issue. So surging, to define that real fast, that is a reversal of flow through the impeller. The impeller doesn't reverse rotation, but the refrigerant reverses back through it from the discharge into the suction. This is because it's an aerodynamic compressor, meaning it is non-positive displacement. Other compressors like scroll and screw are positive displacement compressors. They can just directly compress and overcome those high lifts in ways that centrifugals cannot. So surging is something we deal with a centrifugal, because the refrigerant does have the ability to reverse flow back through the impeller, which is very harmful. Now, a high ratio or a high lift can or is what will push us into that surge condition, but that value of what creates that changes as our load and operating conditions change. So when the chiller is at a low load condition, the amount of lift that chiller can operate under significantly reduces, and it is much easier to push into a surge because of the lower lift threshold. So they're not the same, but they are very much correlated, and it's not just a head pressure issue. We could be having a low pressure issue on the evaporator side. We could have a flow issue there. We could have a refrigerant issue. We could have oil migration issues. Those things will also force our lifts to be higher, even though we don't have a high head, and that's going to push us into that surge condition. But that I just want to emphasize that surge point will change as our load and operating conditions change. So the more load we have, the more flow we can push through that impeller, then the more lift we can overcome with that centrifugal compressor. And that's where they begin to become disconnected or decoupled from each other, and they're not that directly correlated, but they do heavily influence one another. And I really hope I'm saying this in a clear enough way. I'm trying to really bring the concept down to make it easier to grasp, but it's, yeah, hopefully that helps. But that I want to summarize this. Let's try this. Your ratio is equivalent to lift, but just said in a different way. But your ratio, or your compression ratio, or your lift is not the same thing as a surge or is surging. They are two separate things to evaluate on their own. Okay, I do my best. All right, let's get into some of these chats. I've been kind of watching it. I see Jason's in here causing trouble. Come get you, sir. I would like so how to let's try how to remove POE oil scent from working clothes. I'm going to throw out another working set. I should maybe get my wife in here to help answer this one, but I think I can do her justice. I think. We're going to try. Okay. How to remove POE oil scent from working clothes. I'm going to throw out another working set. So, her actual favorite way, like if we've got clothes that have terrible smell, so with us, we deal with oils and such. Hers is what is it? White distilled vinegar, or just white vinegar. Either way, she will put some of that in, and these clothes get washed by themselves, right? So when I come in, and I've had that one, just one of those days, as we all deal with, that's usually what she uses. And I think at some points, I think she may have used like some baking soda powder or something to that effect. I'd have to, I want to, I'm not 100% on that one, but I know for sure one of her go-tos is using that vinegar. And from what I understand, she will do a load with the vinegar in there, and that will do a lot to break down those oils and the smells. And she may have to do it sometimes 2 or 3 times, depending on how bad it is. And then once that's done, she will then run the load with the regular detergent to help flush the vinegar out and like just do a proper clean. But by that point, I from the way I understand the process, she's already kind of gotten the oils to extract out of the clothes, and it just needs to be cleaned in general by that stage. So that's my understanding of how she's doing it. And if I'm off on that, then she's got some voodoo that don't ask me. Wrong guy. Sorry. I think I saw somebody had a comment about clothes in here. No? Okay, never mind. Let's see, what function of saturation? Please measure in saturation and condensing. What's function? How to measure? Okay, yeah. I think I understand this one. Let me give him my best swat. All right. What function of saturation, please, how to measure in the saturation in condenser and evap? So saturation, so we're going to get into some just basic principles here. Saturation is the boiling temperature or condensing temperature of a refrigerant. So just like with water will boil at 212 and then condense at 212. Now we could get into sensible and latent heats and all kinds of stuff there, but the point is that is the point at which it's going to transition states. Okay, we're going to move from a liquid to a gas and from a gas to a liquid. That is our saturation point. And that's what we're doing with the refrigeration cycle of how we're able to move heat. As we move from one form to another, we are adding heat and rejecting heat, and that's how we can take it from, say, the evaporator, which in our case with the chiller is water, right? We can take it from water, put it in refrigerant, and then either move it to somewhere we can put it in air or other water to cooling tower, whatever the case may be. So every refrigerant has a PT chart, a pressure temperature chart. If the you'll have to find, like, obviously you should know what your refrigerant is, like what type it is. Is it 123, R11, R22, 134? So once you know what type it is, you can pull up a PT chart for that refrigerant. And that PT chart, pressure temperature chart, will allow you to take a pressure reading of the vessel. Okay, so let's say this was the evaporator, doesn't really matter. You take a pressure reading, and then you can use that chart to correlate that pressure to a set temperature, a saturation temperature specifically. And that temperature is how we can determine how well we can use it for a lot of things. One, we can use it to determine how well we're transferring heat. We can use it to see where we need to be to move heat. So it, like how much we need to lower the pressure. So if we want to have a leaving water temperature of 45 degrees on the evaporator, and we have a chiller that uses a 3-degree approach. Okay, so what that would mean is that with a 3 degrees of approach and we want 45 degrees leaving, we need the refrigerant saturation at 42 to achieve those numbers. So we can then, by using the metering device and the compressor, and these two working in unison, we can control how much we feed into the evaporator to achieve a set saturation temperature so that our leaving water temperature can be at set point, whatever that set point is. Now, that is a very oversimplified way of explaining that, but in essence, that is what is being accomplished. So we are always moving from more heat to less heat. So in the evaporator, we need that saturation temperature, you'll see on the PT chart, to be lower than the water temperature. And then on the condenser side, let's say it's a water-cooled condenser, for example. Well, we want to reject heat that way, so we want to get rid of it into the water in the condenser. So that saturation now needs to be so much higher than the condenser water temperature so that we can move enough heat at a high enough volume to get that into the water to then be carried off and gotten rid of somewhere else. So that is how we're using saturation and how we can determine it with just a pressure gauge. Whether you have a control panel giving that information to you as a readout or not, just depending on what equipment you're working on. Like that is what saturation is, and that is what we're doing with it. All right, let's see. RTC troubleshooting and service procedures. Does Trane have a good... So Brad, I haven't been through Trane's RTAC sessions on troubleshooting their equipment, so I'm not sure. I do know, from what I understand of Trane, they're very similar to York in their classes. They are worth taking. One of the struggle I have with a lot of those classes is the first couple of days is just basics anyway. Like, you're just covering the same, this is what a chiller is, this is what it does, blah, 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 blah. Same refresher on that side of things. And then the last little bit of the course will be, hey, let's actually talk about this specific machine that you're here to discuss. So that's one of my criticisms, I would say. Some of them have gotten better they'll have you do that beginners portion online now, and then the in-person that you show up for will actually just be focused on that specific machine. So I've seen that change since COVID, I would say. That started to become a more common practice with them. But in terms of the RTAC, yeah, I'm not sure. Hopefully somebody can jump in and give you who's actually been through that class. I personally haven't. I have a question. My hand is ready. What makes a YK chiller surge regularly? Okay. These are good questions. Here. And the YK is a good one to discuss, because it does struggle with it. And we can talk about why. Okay. What makes a YK chiller surge regularly? So YKs really like lower lift values. And what I find is the YKs that struggle with surge the most usually are not being fully loaded to begin with. So a YK can handle really high lift without issue. But they've got to have the right load conditions to be able to do that. You've really got to be able to put a load on that machine. And load is not just strictly, do you have the temperature difference? Just because you've got, say you're trying to achieve 45, just because you have 53, 54, 55 coming into the machine does not mean that you've actually got that much load if your GPM is low. So that is one of the big things to verify early in that troubleshooting process is, what is your GPM at the time? Do you have enough GPM? Are you flowing through that chiller at an adequate rate? Because if you're not, then even though you've got a high temperature difference, you don't actually have that much load going through the machine. And so it can't load up. It can't open the PRV and if it's variable speed, speed the compressor up very much. If it can't do that, then you're going to struggle with surging far more often because the compressor can't load. And then if you are not keeping your condenser temperatures down, your condenser water temperatures down to help with the lower lift, then it's going to continue to struggle. Okay, so that would be one of the real early things I would want to verify is what is my actual flow, because it's one of two things. Either we don't have a whole lot of load, or we don't have proper GPM, or some combination of the two. And with that, and the compressor is not staging up very much because of that, then you're going to deal with surging far more often. And with the YK is one that I try to run as cold of water as I can through it. I know that I've seen comments where I've talked about this in the past, and it sounds like I'm buying into engineering, pitch and speak and stuff. And maybe, you have your own experiences, but I know if just from my practice and my training, like YKs can go down as low as 60 and have safe operation, a 60-degree condenser water temperature. And I personally only push it to about 65 just out of my own habit, even though they say I can go lower if I want to. But that is one of the key goals that we're trying to do. We're trying to get that condenser water temperature down to help minimize that surge. Because what you're doing is, by lowering the condenser water, you're lowering the lift. That is what you're actually doing by achieving that. It's not just, just lower your condenser water. What you're doing is you're reducing your lift, which is going to help that compressor with that load condition. Now, if you can get that compressor to actually load, and you've actually got a loaded state where you've got good GPM and you've got good load. So most of these machines are designed for a 10-degree delta, give or take 2 degrees. So if you're pushing 8 to 10 degrees through there with proper GPM, but you're still struggling with lift with a machine that would otherwise have pretty good load, well, okay. So then we get off into a whole nother world of, is our refrigerant levels good? Is our liquid level sensor controlling correctly? Is it calibrated correctly? What is your liquid level set point? That's one of the things that I see is the liquid level will be used, the liquid level set point will be used as a means of trying to overcome other issues. Like I've had YKs in the past, they were struggling with surging and high lift with the and so what they did to compensate for it, and this was a factory technician that did this, by the way, they lowered the liquid level set point so that it wouldn't build as much pressure in the condenser, and that was fine. It just left it at that. Well, what I found was when the plant had a staging issue and it didn't have proper isolation on the condenser water side, and so when one of the other chillers would be told to shut off, one of the lags, and that chiller was left in lead, well, it would also shut the lag pump off on the condenser water side, which dropped our GPM. Even though we were still flowing through 2 barrels, we dropped a pump out, and which essentially cut our GPM almost in half, which then we started having surging issues. We'd bring that other pump on, everything, all of a sudden, as long as the lag chiller was running in conjunction with the lead chiller, the YK at the time, it was running fine. Well, that was a flow issue on the condenser water side, right? So essentially, we just, until they got their isolation valves addressed on the condenser water side, they couldn't shut down both pumps in that particular plant's setup, right? So that becomes a plant issue. But when YKs as a whole have a reputation for having surge problems, and so every plant may have a different reason why that YK is surging. It could be load here, could be refrigerant set points there, could be low refrigerant here, could be low flow on the condenser here, low flow on the evap there. All of these contribute to what makes a YK surge, and like they ride that surge line quite fragilely, in my opinion. But there's not like a blanket copy paste explanation as to why each YK is surging. So Now, one of some of the reasons why a YK is so prone to surging, that comes back to even just the compressor design style. So, one, it's a single impeller. Single impeller compressors, the complete lift of that compressor is being put into one single impeller. You don't have a multi-impeller design. You've just got one, which then puts a lot of work on one impeller to manage, in some cases, a lot of lift. And we see that a lot of other manufacturers have moved to multi-impeller designs or multi-stage designs, where you'll have 2 or 3 or more impellers stacked in series with one another. And so the discharge of the first impeller feeds into the suction of the second, and so forth until we make it to the condenser. We see that those compressors have less issues with low lift or with low load. They have less issues with surging because they can handle that high lift better. That's what we see with a multi-stage compressor. But part of the issue is those compressors have a harder time unloading at the same levels that we see a YK can do, and they also, depending on the conditions, it may not be quite as efficient. And that was one of the arguments to a single impeller is if everything goes correctly, you can achieve a very nice stable efficiency that a multi-stage may struggle with. But a multi-stage can handle lift conditions that a single impeller compressor will struggle with. And that becomes kind of the trade-offs you have between the two. So, yeah, as to one reason why a YK will struggle with surging more than other compressors on the market is because they are using that single impeller design compared to where most others are actually using a multi impeller, or many others. Now, they're not the only one with a single impeller out there. With any surge, though, like beyond just a YK, we have to verify our basics, and we have to be careful that we don't prescribe the same issue too broadly across different scenarios. We have to verify that our flow and GPM are correct. We have to verify that our refrigerant charge is correct, and in a YK's case, set correctly. In a YK, you want to see about half glass, 1/3 to half glass on both evaporator and condenser, especially at a full load. So if you are getting that machine to load up at all, like those sight glasses should be able to balance out right about there. If you see significantly less than that, maybe the evap's good, but the condenser is just not, you might have a charge issue. That could be contributing to some of your surging problems. So, yeah, flow, refrigerant charge, load. Load is going to have a major impact in that. Again, we're not going to be able to maintain the same high lifts that other compressors can with a YK at lower loads. So, a CVH, for example, by Trane, they can manage some pretty low loads but a pretty high lift at the same time. Multi-stage compressor. But we can't run those same low condenser temperatures, and we can't unload, like the CVH cannot do the low end of what a YK can. It just can't. It's not built to operate at that. But in my assessment, in my experience, the CVH can do really well at the high end. And it can manage those really high lifts without issue. And so it just kind of, it depends. Anyway, go to your basics on the why is it surge regularly. We need to verify the basics. At some point down that line, if all the basics are truly 100%, you may have a compressor issue. But it sounds like you're probably running into multiple YKs based off of how you structured your question. So you're probably seeing multiple YKs, and many of them have surge problems. Comes back to the basics. We have to verify the basics. Okay, a lot of my major surging issues I've had with any machine almost always related to one of those core basics being off and just addressing those basics. All right. Filling up 550-ton chillers with water-side economizers. So it's going to take a while. But yeah, good to see you in here, bud. Why don't you do more videos in the field? Can we get more videos from you in the field? Yeah, no, it's a very fair question. So why don't I have more videos in the field anymore like I used to? It's because I'm not in the field anymore. I have committed full time into doing Chiller Academy, training, educating. So I spent over a decade in the field doing this every day. Have just worked my way into this position, if you will. This was always the dream. This was always the plan. Now, Chiller Academy itself, came along as I went. I didn't really have that side of the plan figured out, but as a whole, this was the direction I knew I wanted to go in my life. So, yeah, I don't post those anymore because, well, I captured 6 years of it, and I know the vlog, see everything every day, kind of fun is really interesting, and I enjoy that stuff too. I watch a lot of everybody, like Chris Stevenson with HVACR videos, right? It's fun seeing the field stuff, and I've got 6 years of that stuff documented on my own side that you're welcome to watch in the history and the library of stuff. If you want to see more current stuff, I would say, Jason here in the chat, Jason Johnson, he's doing a lot of that. He's showing a lot of the everyday life. And so, like, if you want to see more of that live side of things, more than just education at this point, like, he's somebody you could follow. Like, my main goal here is to educate and build and answer these questions. And I like, entertainment matters, and seeing somebody else do it matters a lot. Like, it does matter a lot. It's not just entertainment. I don't want to undermine or be too critical of that position. It's not just entertainment. I am greatly helped when I can actually watch somebody else who is skilled at it actually do it and do it successfully. That helps me feel more comfortable in what I'm trying to do and my approach I'm going to take. So that's what that 6 years of what I have done is there for. As best I could document it at the time, given my life circumstances. And so, yeah, you're not going to see a lot of field stuff from me going forward. I'm okay with that. And I would encourage you to go support somebody like Jason if that's really what you're focused on. And what I hope is that more people like Jason can step up, can start putting content out there of your daily life, and then allow someone like myself to be here and to help answer the questions you have about what it is they're working on. I know from firsthand experience, it is impossible to actually capture a job site, what you're doing, and explain everything. I've tried to do some of that, and like, it is really freaking difficult. So if these guys can get out there and really show what they're doing and let you see the day-to-day from their perspective, and then let me help maybe fill in the gaps that they just didn't have time to explain. Like, they're just not going to have that. Like, that's not why they're there. And I've been in their shoes. I know how it is trying to capture and show other people what it is you're working on while also explain something along the way. It's really freaking difficult. So that's where I think I can help fulfill that role on this side of things, and others have already stepped up and began filling that gap on the day-to-day life side of things. So that's why you don't see field stuff from me anymore, and it's why you're not going to. I have transitioned into the role I want to fill to help us move forward as a trade and as an industry. And I want to see others continue to step into this mission, and all of us work together to accomplish this. And Jason is definitely one of those that I would recommend in that process. TU software only used for binding. Any other purpose? Please explain. Okay. All right, TU software only used for binding. Any other purposes? Please explain, sir. Yes, so TU, the binding is one function it has, absolutely. Its other side is it can do like a data log capture. So a very common practice, especially on the factory side, you walk up, you plug in, you pull a log. Capture that machine, you can analyze it, you can do whatever it is you feel like you need to with it. My image has frozen here. 1 second. There we go. That was weird. Anyway, so we can, so you can take the data log and analyze that, right? So that'd be one function. Another function would be commissioning. You need to have TU to be able to plug in to the UC controller for commissioning purposes, configuring the chiller, things of that nature. So those would be kind of the three primary things. Data logging and just taking a system analysis, commissioning the system if that is needed, and then as you mentioned, binding. Those are the three primary purposes or functions that I would say the TU software serves for us. And it looks like we're having some internet issues today. If you don't worry about if you're going to miss anything here, this stuff will get loaded up and posted separately. So if there's a spot where I'm saying something and it starts cutting out, don't worry. I will get this stuff re-uploaded. I apologize for that. I'm way out in the sticks with where I live, and we've got pretty good internet as long as it works, but that's with the caveat that as long as it works, and sometimes it doesn't. So I'm sorry. I have talked to them about it many times. How do you start up a chiller? Oh, how do you start up a chiller? That is a loaded. No, it's not a loaded question. It takes a lot to answer that one. Okay. How do you start up a chiller? You got to try to make sure everything's buttoned up. So one of the first things that should be done is just visual inspections. Is all the piping done? Depending on the type of system, the installation may need to have already been completed, and what just how critical the operations are for analysis. Need to make sure there's not any damages to anything. Some of this stuff should have been inspected before it got installed and before it went through when it was received. So, but you as the commissioning person, especially if you're doing a commissioning report that's going to be sent to the factory, as we sometimes need to do, and then you're going to be responsible for documenting all that stuff. And if there was damage done and you didn't report that, then that is on you as the commissioning tech. And I'm going to take your question from how do you start up from a commissioning startup perspective, not a turn it on. Because if it's just turn it on, then you need flow, you need safeties, you need a call. Once you have flow, safeties, and call, and you've got enough load, okay, I guess that'd be the fourth thing. So if you've got those conditions, the chiller will turn on and run. And if it won't, well, then you got to just troubleshoot from there. That could go in an infinite number of directions. But yeah, so as a commissioning tech, you've got to document all that stuff. That becomes your visual inspection. Now, once you go through the visual process, you're happy with the piping, all the sizes are right, everything looks like it's set up correctly. If you got any strainers, any valves in place, those are in proper condition, working order. You'll want to make sure one, software is up to date. So sometimes there may be software revisions to the software you'll need to do in the field. That'll just be something to verify. Most of the time, that's not going to prevent you from doing a startup unless that software version had a major bug, but usually the manufacturer will be involved and will make sure you've got that updated software, because they know which serial number has got the bad one, and they'll make sure that whoever the commissioning tech is, they've got the correct one, and they know ahead of time, hey, we already know this software needs a patch. Here's the patch. Upload it whenever you go to do commissioning. So you'll do that. And you'll verify all your sensors. You'll leak search. So by sensor verification, all your temperature sensors, pressure sensors, anything that's on there, you want to verify all of them. Make sure everything is reading correctly, accurately, it's scaled properly. So that's one of the things with like an MCS panel. If you're dealing with like a dumb bush, you want to make sure all your scalings are correct. You've got the correct refrigerant programmed into the chiller, because sometimes that may come programmed differently, and that's not just a Dunham Bush or MCS thing. That's across the board. You want to make sure that all your settings and configurations are what you know the chiller is supposed to be. If you're doing a commissioning startup, you should have the data sheet or the design data sheet on that chiller, so everything should match up to that exactly as it says. If it didn't, somebody screwed up. But make sure that your all sensors are within tolerances and the panel's configuration is correct. All the boards that need to talk to each other are talking to each other. We can disconnect our motor leads and do some dry fires to make sure that that is correct. Our phasing on the electrical is correct. We have proper phase and rotation, which you can do that with. They've got meters now that you can hook up your 3 leads and verify the polarity on the wiring to make sure that you've got a clockwise rotation. As long as you do, then you're good. So that would be electrical, sensors, the control panel. Once you've and leak search, make sure you leak search, not only for water leak, but refrigerant leak. And then this is saying that the chiller come pre-charged. You may have a condition where it came with no refrigerant in it. It came dry. So in the circumstance that it came dry, you'll have to pull an evacuation and pressure test, pull the evac, go through that whole process, then charge all the refrigerant in. Let's see. I'm just trying to do a rapid fire down the list of just things we have to do for a startup commissioning. This becomes extremely specific as we dive into individual models. So all that's been verified. We're ready to actually turn it on. So then you're going to go through, if it's an air-cooled system, you're going to stage all your condenser fans, make sure those come on individually. Each one of those is working. There's not any failures there. None of them have any bracket issues from shipment. If you've got a water-cooled system, make sure all your pumps are working. Your GPM and flows are good. Even with an air-cooled, make sure your evaporator GPM is good per what the DP needs to be for that particular heat exchanger. And then just turn the thing on and actually verify your parameters. Some chillers require field calibrations. So there's quite a few where it'll have a service valve, but it will come closed. So like a Trane CVH, the eductor has a service valve on the evaporator. It will come closed, and you've got to open that, I think, like a quarter turn or so, up to 2 turns total, somewhere in that range. You've got to, and that's something you tune in. Same thing with some Dunham Bush chillers. They come with the valves closed, and you've got to open them so far and tune that recovery circuit in, so where you're pulling in enough, but you're not over drawing on the evaporator, pulling in a lot of heavy liquid refrigerant. So those are things that we have to field calibrate, or where your liquid level sensor needs to be set at for a YK. That has to be field calibrated. Yes, basically you go into the model specific field calibrations. Here's all the things that we need to calibrate on this particular model, depending on just how it's designed, what it does, what you need to do. Most of the time your install or startup or IOM literature will explain many of these things. Sometimes it may not. That just comes back to your training, your experience. And if we had a specific model to talk about, we could get into more of those specifics easier. Yeah, so it's just a tuning operation. Once you get to the point of actually turning the chiller on, then we're just trying to tune the chiller, right? The field commissioned items need to be field commissioned. We calibrate our flow sensors many times. So many times the flow sensors will need a little bit of tweaking on your specific plant. And keep in mind that needs to be done while we're close to set point on where we're going to be on the evaporator side specifically. So, yeah, you don't want to calibrate that with a hot pull down or a hot loop. You want to calibrate that when we're in the basic temperature range we're normally going to function in, so that we get an accurate calibration on that electronic flow sensor. I think I covered. I mean, that's the majority of stuff we need to do during a startup commissioning. As a whole, it's a pretty broad question, but there are some consistent things that we need to do between all the different chillers, and then we just get into the characteristics of what makes that chiller unique in its own way. All right. Hey, Holden, when reassembling a coupling on a York YK centrifugal, do you need to preload the low speed thrust or either side motor bearings when reinstalling the hubs? So with that question, Jacob, I'm trying to think through when you say preload. I'm trying to think where you're trying to, what you mean by preload. So preload could mean getting flow on the bearing side, but we don't have to do that. To answer in a short, no. Typically, as long as your bearing assemblies are put back in your so at that point you need to reassemble. So you're potentially getting into a alignment phase. So you need to verify that your alignment between the motor and the low speed shaft are good. So you'll do that with a dial indicator. I think there are some laser alignment rigs that are small enough to actually fit in there now, but most circumstances, I've always had to use dial indicators because the laser alignments I had available just weren't small enough to fit inside of that D housing. But yeah, as long as your alignment is good, then yeah, you'll put the collars in, you'll put the coupling in, and then you'll have the torque sequence you'll have to go through. But I'm not aware of any like preload on the bearing or anything. So I guess you're probably talking about the axial in and out. Okay, so that would make sense if you're referring to like the axial load in and out on the low speed thrust. No, so I haven't. That's not a practice I'm aware of. You have to do where you have to like try to push it in, pull it out, or preset that axial distance. It's a pretty small distance to begin with already, but usually just putting that coupling together, it's going to draw all that together regardless. So I wouldn't be too worried about that. I know videos. Yeah. Recently, I've had to clean several cooling towers. What precautions is recommended for safety? Here's stories about legionella. Yeah. I want to do this. Yeah, PD, I think is how you pronounce that. Yeah, with cooling towers, we want to, yeah, Legionnaire's disease or Legionella bacteria. We've got to be very careful with that. That's an airborne bacteria that will get into warm, uh, the warm sump of the cooling tower and will become airborne. It it is an extremely lethal bacteria, and it doesn't take long. You'll become extremely sick very suddenly, and it is difficult to treat. I am aware of cases where people were treated successfully. There's a lot of people who weren't. So if you are doing cooling tower work and you suddenly get sick, especially if you're working on a very nasty tower, um, you need to go see the doctor quickly, like very quickly, um, because and you need to let them know that you have concerns about Legionnaires. That way they can test and quickly get it addressed, because if it is and it's not handled very early into the process, it's extremely difficult to get you back from it, from what I understand. I'm not an expert on the matter. I just know enough to be careful. Now, what I have done, um, maybe I should throw this one up on the. One second. Nope, that was wrong. Come on. Work with me here. Work with me here. Dude. Me and technology, as usual. Okay. Fit this in here. So what I have done is, if I walk up to a tower that is in really poor shape, has a lot of growth, a lot of algae, a lot of buildup, I will recommend that we have the tower shocked, a shock treatment done. So what that looks like is you'll have a chemical contractor come in and they'll do a shock treatment. So they've got a combination of chemicals they can pour into the sump. We'll get it flowing, and they usually tell us to give it a couple of days, let that treatment get in there. That'll just be take the recommendation from your chemical treatment guy you're working with. But we'll shock it, and that will kill any extreme or dangerous growth. Has been my experience. I guess this is what I've had to do many times over the years. I've never personally had a trouble with it beyond that. Um, and so after the shock procedure, you can then drain it down, get in there, pressure wash, and clean the tower. Um, Now, one of the things that I've heard, I've never had training around this or practiced it, but there are some places that require you to wear. It's almost like a hazmat suit. You'll have a full body garb and a respirator assembly. I know a lot of people recommend, if you're doing tower work, especially on a tower you're not familiar with or has any kind of potential at all, wear a respirator with it. Full face is what I've heard recommended, or at least the mouth and nose, so that as you're breathing, you don't have potential of inhaling any kind of bacteria from the tower, even if it's not Legionella. So yeah, from a safety precaution, those are kind of the two directions. And I know I've talked to some that firmly believe that no matter what, whether it's a clean tower or not, you should be wearing a respirator assembly and some kind of like clean hazmat type suit to protect yourself from any kind of growth. And I don't think that's not a bad recommendation. I personally have not practiced that, so I cannot speak to that from personal experience, but that is something that I know is very heavily recommended out there. Now, yeah, my go-to is doing the shock treatment, and usually by the time that's completed, I've personally felt comfortable in doing that whole process. I've never had anybody in my career come down sick with Legionnaires. Um, And anytime we've had any concern at all, like that has just been the default. Hey, this is a nasty basin, nasty tower. This is terrible. We're going to have treatment come in and do a shock on this before we get in there because it hadn't been maintained, and who knows how long chemical treatment hadn't been kept up with. Like those are things that we're trying to evaluate. But if you want just a complete be safe no matter what, that's where the respirator, I think, is the main thing that they talk about. You just don't want to breathe that bacteria in. So having a full respirator to help with that, to filter those bacteria out. For the peeps with compressor oil, I just bought a different washing machine to keep work outfit separate and use the oxy stuff there. Okay, yeah, and a bit of vinegar. Yeah, I see that. Yeah, so Supreme Ruler there. We bow to you, sir. So I've heard of the OxyClean. I know, and the vinegar. So you use vinegar too, yeah. I know that's the primary thing my wife uses is the vinegar in the wash. Thank you, Jason. I see you there. Please make sure. Too much current leakage to ground. Yes, slip seal. How do you start and shut down a chill? Yeah, we've talked about that. Needed a computer to cut it on and off. Read some of John's books, Mark. Sorry, I'm just kind of breezing through the comments here, kind of trying to catch up. Read the manual of that unit. Lift. Yeah, I'm not a fluent speaking engineer. That's funny. See, thank you for your hard work every day. Just remind you. Oh, thank you. All right. Sorry, chiller has nothing to do with starting a car. 19% about starting a chiller. So I see we're getting into a tiff. I need PO for some clothes. One load white vinegar. Oh, okay, everybody. We saw my wife get into the chat here. She heard me talking from the other room. So if you haven't seen that, she says one load with white vinegar. If bad, second load baking soda and detergent. That is her official strategy, and it has been very effective. So, yeah, you see the Natural Lioness comment there. That is the official from the lady herself. As she heard me butcher her process. Just call Centos. Oh, we require an intro to HVAC course before in-person training. What is the difference between cooling tower and chiller? Ooh, okay. This is a good distinction. Let's talk about this. Because I've actually heard this pop up a couple of times. And, these aren't bad questions. They're just questions that some of us haven't had in the same way. And just not something you always think about. So it's yeah. What's the difference between cooling tower and a chiller? So how I define a chiller is a piece of refrigeration equipment that has a hydronic evaporator. That is a form of chiller. Doesn't matter the type of compressor, doesn't matter the type of condenser. None of those things have any effect on whether it's a chiller or not. If our evaporator, it has a hydronic function, meaning it's using water or it's using a brine water, glycol water mixture of some kind, regardless of what's flowing through the evaporator, we are cooling a fluid. a water of some kind, hydronic based, then we have a form of a chiller. Now, this scales from teeny little process chillers that might cool a CT machine all the way up to, the biggest of the centrifugal that exists out there. So, like, that is my basic definition of a chiller. Now, cooling towers are used on a variety of applications. In a chiller context, we use it to cool our condenser water. So we have a water cooled condenser that we're flowing through. Now, when we say water cooled, it could still be a brine mixture, meaning that it has some kind of glycol or other non-freezing agent included, so it can run at lower ambience safely. But we'll have something like that running through the chiller to take the heat away, and the cooling tower will specifically be located outside to reject that heat. Now, cooling towers can be used on a variety of applications. We could use it for water source heat pumps. We could use it for self-contained equipment where basically it's an indoor air handler with all the refrigeration built in, and we have a water-cooled condenser, and that water-cooled condenser just pushes the out to the cooling tower all the heat. Cooling tower throws the heat out, sends cooled water back to the condenser. But all the evaporator, those aren't considered chillers because, like with a self-contained, you still have a air over evaporator coil. We're still moving air across a coil through. It's an air handler with a blower. Like all that process is still happening. So it's just a regular air conditioning system with a water-cooled condenser. So cooling towers are still used in other applications outside of just chiller equipment. But essentially, a cooling tower is just cooling water, but it's usually condenser water specifically, or it's water that we're using to cool a condenser. Now, we could get way off into the weeds on specialty applications and how they can be used as an economizer function. Then we start talking open loop and closed loop towers, and like we could get way off into the weeds here. Sorry about the mic there. But on a basic level, that's what it's doing. It is not a sub device, but this cooling tower is serving the chiller or internal cooling equipment by rejecting its condenser heat instead of having an air over condenser coil or something to that effect. That is what our tower is doing, and that is where they're separate. So there's usually not any refrigerant. Under a basic application, there's not refrigerant flowing through a tower. That would be a remote condenser, and there are those. So we do have things like remote condensers where we have a system similar to a self-contained where all the basic components are inside, but the condenser has been moved to an outside location somewhere, and we have refrigerant piping running out to that remote condenser, and it is actual refrigerant in a little air-cooled coils sitting out there with condenser fans. Like those also exist, but those are not considered towers. They're remote condensers. So when we say a cooling tower, we're referring to something that is processing condenser water in terms of a chiller. And then it gets far more specialty applications from there, as we can use it in various ways. And the style of tower then plays a part into what all it can do in its own context. All right, no compressor acceleration on a CVH. Top too much air. Let's see.
There was a second comment, but YouTube stole it.
Oh, did it?
So you can also tell them about RLR off Amazon with
Okay.
the detergent. And if that doesn't work, then again, baking soda.
So I'm being told RLR from Amazon
I'll
is another form here. We're having a live coming into the newsroom here, straight from the source herself. Okay. So compressor won't accelerate. Yeah, the 638. I see your comment there. It's not quite enough information to say the compressor won't accelerate. There's it's just a little too broad to try to dive into. And assuming is just too much air, too much non-condensables would be a technical way to say that. It has a lot of non-condensables, so it's running at high head pressure, something along those lines, or it's pushing up against the surge boundary. That could be a problem, but we're going to need more information to dive into that. If we had a little bit of operating data or something thrown in there, that might help us kind of talk about that on a more consistent level. Yeah, welcome, Luke. I see a comment there. I'm starting to catch up on the chat here. We've got a little bit longer. We'll keep going here, so I can take a few more questions. And if I don't get to all the questions in chat, by the way, I will save the ones I don't get to. So feel free to just go ahead and get them posted in there. I'm trying my best to move through them as quickly as I can, but I will save those questions into the log of questions I haven't answered yet, and they will get answered as I can best do so. I do have a question about how you can work on Trane without being a Trane tech. I thought they locked up the software to the point where you couldn't do anything without paying them a bunch for a laptop guy. Aha. So, let's talk about this. All right. How you can work on Trane without being Trane tech. I thought they locked up their software to the point you couldn't do anything without paying them a bunch for a laptop guy. So there's a lot you can do without having to run through the software, especially if you have access to the lid menu, the LLID menu, which is binding, which is the main reason, in my opinion, you really need the software at this point. Like, in my experience with Trane chillers, almost all the troubleshooting we need to do on a routine. Now, we get off into the weeds on different stuff, okay? So there are circumstances, but the vast majority of it we can do if we understand the chiller well enough, okay? So there's our big caveat. We have to know the machine. But we can do these things without needing the software. Now, something we can't do is bindings. We have a bad sensor. We need to go through the binding process. Trane has gotten so much pushback on this that they did build in a option to do that in through the control panel. But that option does have there is an ability to turn that off to where you can't access it. So if they did that, then the laptop software is literally all you have. Now, if you can build a relationship with the right person, and I have found that comes back to having a salesman or somebody inside of Trane that you do a lot of work with, and you can build a relationship with your local Trane office, you might find somebody who's willing to license you a copy of the TU software. You can download it for free from their website. You can have the software for free, but it's useless if you don't have an active subscription. And it's a little bit of a process to get that subscription because you have to get the computer ID number, send that to them, and then they generate a serial code based off of that ID that they have to then send back to you. And it's only good for that one device. And if you have to change devices, well, then if you have still an existing, like if the laptop crashes for some reason, well, then you have to reach back out to that person, and then you have to have them resubmit a code, and it just, yeah. There is a way. You just have to have somebody from Trane willing to sell that to you. And it's not cheap either. It's cheaper than having them show up and do it themselves. If you have to do it enough times, absolutely. And that is, so I could get off on a tangent as to my thoughts on this as a whole, and I think the manufacturers are doing them a disservice by going this path, but without ranting here. yeah, unless you're needing to replace the sensor or unless you're commissioning the chiller, you can do vast majority of everything you need to do on a routine. And if you have access to the binding screen through the display, you don't even like. There's very little you'll actually need them to show up and plug in with a laptop for. Very little, in my opinion. Now there are some people, and I've seen where Trane techs, they're very dependent on the laptop software, and they're trained to really utilize that software heavily, and that's fine if you choose to work that way. It does display the data in a very efficient manner, right? So there may be, like, if you're used to just looking at the data through that format, then not using it could be very cumbersome, but the data you need to troubleshoot is still present in the display without any special accesses or anything like that. It's just the default display. It just means knowing what to look at and getting comfortable toggling through the screens efficiently. That's really the challenge that you've got at that stage. So, yeah, try to make friends with somebody at Trane to get the TU software. Do the best you can there, and you can still do a lot of the work you need to do. You can still troubleshoot. You can still diagnose a lot of stuff. You do still have some manual controls. Like, not all manual controls are locked out just because you don't have the laptop. Now, there are more manual controls inside of the software on the laptop. You can do more in there if you needed to, but most of the time, if you know how to manipulate the chiller, which I know that's a caveat to what I keep saying, you have to understand the machine. That's going to be something no matter what you do. You could have 100% access to everything and it all be free, like we had with TechView, right? TechView was completely free, completely open. But if you don't understand the machine, it doesn't do you much good anyway. So I think the bigger issue is understanding our equipment effectively and knowing how to work on that machine and just how it functions is far more important than necessarily the software itself. Now you could throw in examples like a turbo core. So if you don't have SMT and the access with turbo core, well, you are kind of screwed there, right? That is a good counter argument to what I'm saying. It's hard to work on a turbo core without the software. It is. But I don't think that is true for a CVH. It's not that it's not the same. I'll just say it that way. So long term, I do think these manufacturers are going to. I think they will have trouble because of this type of stuff, and the manufacturers who don't require this, like Daikin, like Dunham Bush, two examples, they're going to really have. And I've already seen this. They become the premium choice strictly because their machine is more open to work on. And the companies that they're buying the equipment from majority of the time are letting them know, hey, we don't like that machine because we can't work on it. And your service bill now significantly increased because we have to call them out to hook up, plug in, do whatever. We can't do it ourselves anymore. The more they do that, the less customers are going to want to work with them. And that's been my experience. That's not even my opinion. That is my experience. They've been on this road for some time. I think eventually the markets will pressure them into figuring other things out. I think the fact that the binding screen exists is an example of that. I know York has gotten a lot of pushback for their access manager, and Carrier has gotten some pushback for their stuff as well. And we have seen some software revision updates that have kind of relaxed some of these things a little bit because they got so much pushback. I think it's ridiculous that York is charging people a subscription basically for having access to like the back end of the software to service the chiller side. So if you have the access manager tool and you're a technician who has had like you have to, like for the YK, you have to be within 3 years of your last certification. So you have to pay for recertification routinely. And then for every chiller you have in your profile that you are working with the property on, you've got to pay additional fees to have that in your profile and stuff, right? It's completely ridiculous. Um, Give it time. I think this will change. It's going to take time. They're going to have to feel it, and I could spend the next 2 hours breaking down my thoughts on this whole topic. I'm not going to do that, but I could. Yeah. Okay. Let's see. Oh, no R. Yeah, we'll see you, Jason. How to become a millionaire in HVAC. Start a company. Start a company and grow it big. That's about all I got for you. What's your basic procedure for troubleshooting a boiler? Yeah, I'm not a boiler guy. I know enough about boilers to get in trouble, right? So, I mean, realistically, I know enough to where I can successfully run a mid-level call on a lot of boilers. And that's just a part of working in our side. Like you're going to get involved in boilers at some point. At least that's been my experience. So I don't know enough to sit here and try to break that down comfortably. Now, I will say there is a friend of mine, Boyle Earn. He has a similar to Chiller Academy, but for boilers that he is doing boiler education and troubleshooting content. He's also a really good resource on troubleshooting and working through boilers. So if you have a lot of boiler questions or you want more education and research there, reach out to him. He'll be able to help you out. So and that's boilelearn.com. Really, really good guy. Really knows his stuff with the boiler side. So I would recommend him. And I'll stay in my lane on chillers. What is the future of steam in the field? Steam is probably going to stay in the industrial space. I mean, there's still like we've got the SYK or YKS. I forget which way it goes. Anyway, it's a steam-driven compressor, right? So steam's been in the industrial space. The light commercial, or not light commercial, but the light side of heavy commercial and just the heavy commercial side of the industry itself has moved away from steam in my experience. Majority of all these steam that aren't the non-industrial steam facilities that we used to have in my region have gotten retrofitted and converted into regular hydronics at this point. They're no longer using steam. So steam isn't going away, I don't think. Not that I can tell, but it is becoming a more specific, specialized application. What is a good way to determine what a good saturated suction temp should be on a chiller with a chill water loop with glycol? Like with a 35% glycol percentage. Okay. So that is going to come back to your approach. Let's talk about that. Give me a second. All right. And if you hear any kids in the background, it's one of those days, so I do apologize. It is what it is. It'll be all right. What's a good way to determine what a good saturated suction temp should be on a chiller with a chill water loop with glycol, like with a 35% percentage? So that's gonna so we're I would base this off of approach value, which comes back to the type of heat exchanger. So like a braze plate and a DX heat exchangers, those are, I say braze plate, a plated heat exchanger in general, whether it's braze plate or just regular compression plates. A plated and a DX, which means it's a shell and tube, but refrigerant is in the tubes. Those are typically around a 10-degree approach at full load. So, which approach, if you don't know, is you're leaving water from your saturation temperature. So, and this is true on both condenser or evaporator side. But we're talking chill water specifically here, so we'll hone in on the evaporator side of this. So we want to have our refrigerant saturation within a certain temperature of the leaving water for efficient heat exchange. So the more load you have, the more approach you would expect to have, because we're having to transfer the heat at a higher rate or a higher volume, which is going to require it's going to require more separation between the temperatures to get a higher transfer rate. Okay, so just kind of get into some specifics there, but anyway, so yeah, a plated and DX typically around 10 degrees at load. Now that plus or minus a couple of degrees depending on your specific heat exchanger. And then usually a flooded or a falling film design is going to be around 3 degrees at load. So you want to see about 3 degrees or less at load. Now, when you start having a brine mixture or a glycol mixture, that reduces our heat exchange efficiency. So we cannot exchange heat as well once we start introducing those into the water stream, because glycol doesn't transfer heat as efficiently as water does, but it does keep us from freezing. So its whole purpose and point there. So the higher the mixture, the more it's going to increase your natural approach. So with a 35%, that might add a couple of degrees to your approach values. And as that increases to 50%, that's going to add several degrees to your approach values. I don't know of a set kind of rule of thumb that this much extra adds this much, say, efficiency loss. And it also then depends on whether you're using propylene or ethylene glycol bases. So those have different heat exchange properties in and of themselves. One's toxic, one's not, but one can transfer heat better than the other. So then, depending on which type of glycol you're introducing into the system is going to affect how much that dilution percentage has an impact. So there's quite a few variables there. So my short answer is you're just going to have to kind of feel it out, in my opinion. Obviously, the more the glycol is in there, the higher that approach is going to be. How much is too much? For me, it's hard to say. It really is. I'm going to take this from a braze or from a plated heat exchanger perspective, or a DX. This would apply to either of those. So if 10 degree is my typical that I would expect at load, which at part load, I might be doing 5 or 6 degrees and be running really good. And I've got glycol in the loop. Let's say it's at 35%. And so I've got a part load condition. I know that normally part load, again, 5 or 6 degrees of approach. I'm going to add a couple of degrees to that. So I might be looking at a 8 to 10 degrees of approach under part load with 35%. When we get into a full load scenario, so I would expect to run closer to that 10 degrees of approach with no glycol, then having 12, 13 degrees of approach wouldn't bother me, because my glycol dilution is high enough. I would expect that higher approach value. Now, if I started seeing 18, 20 degrees plus, and it started to get excessive by that margin, then I would have to start asking questions and think that there is an issue there. But I would expect that adding glycol to it is going to affect the by a couple of degrees, right? And that's going to be just very variable. I'm sorry I don't have a more concrete response to that you can easily apply. And it is something where you have to feel it out with my experience. I also have limited exposure with glycol systems or brine systems just because of my location. I'm in Texas, right? So we're deep into the south of the U.S. and we don't have a lot of those low, cold, ambient, freezing conditions that you deal with elsewhere in the world. And so we don't have as many brine plants, and so we definitely have them, but I just want to put that caveat in there that I don't have the most experience with brine systems in the world to be able to give you some. I guess part of my point is somebody who sees that more regularly may have figured out some better numbers on how it tracks. They figured out that, okay, using ethylene glycol, 10% adds 1 degree, 20% adds 2 degrees, 30% adds, right? They may have figured that out. I haven't, is what I'm saying. But those are things that I would expect. Hopefully that helps. Okay. Food industry. Please explain solid state starter. Yes. Let's see. Where's our time? Hey, we really need to be wrapping up. Yeah, Bunny Man. I see you've got several questions in there. I know that I've answered at least one, if not two, already. I will cycle back around and kind of add some of these. I am going to grab one more question, and we're going to wrap up with this. Okay. Can you explain solid state starter? So a solid state starter is we're not using let me back up. This is a form of soft starting. That is the core principle to using a solid state starter. We want to do a soft start on our motor, which means that with an electrical mechanical starter, okay, the contactor in a regular split system, an RTU that just closes, compressor turns on, that is an XL starter. It's just a small contactor. And that is true once we scale into a much larger application where we may have a genuine large starter block, but it's just one of them that is a XL start. And XL is literally referring to cross line. So X is cross on electrical schematic. That's what that is referencing. We say X because it's a cross. So cross line, and L referring to line. That is your cross line starter, XL starter. That's the most basic version. That is a hard start. Okay, not a hard start kit with a capacitor and all the other stuff, right? So it is a hard start in the fact that it just slams closed and you get full line voltage straight to the motor, and it better hang on and hold its ass, and it's going to take off and go. So that's really difficult on the motor itself. That puts a lot of stress on it. You have a really high peak in the starting current, right? And it also costs a lot of money to do that once you get to a large enough scale, because starting a large motor like that across line takes a lot of energy. So by having a solid state starter, it is a type of soft starter. So there's various types, but let's hone in on solid state. So what makes it solid state to begin with? Typically we're using an SCR, a silicon controlled rectifier. Now, SCRs can be implemented in a variety of ways. And actually, yeah, let's pull up some photos here. So we've got a couple of styles of this. Let me get this loaded up. Give me a second. Oh, come on. Here we go. Okay. Centrifugal. Let me pull up a solid state starter for you so we can actually discuss it. Okay. So this will be one form of a solid state starter. We have a electromechanical starter. So here's your XL and here's your SCR. So we can use this over here as a better example. So this is one form. This is probably the more common form, especially on smaller equipment. So what we're doing here is we have these SCRs, and in this particular application, we want to use these SCRs to slowly apply power to the motor so that instead of having a huge inrush of current at start, we gently apply power to the motor to allow it to slowly come online. So the way we're doing that is we have our input lead. So we have 3 SCRs here. So in this particular case, be a 3-phase system. Each leg of power, so L1, 2, and L3, coming into post number 1 on this SCR. And we have post 2 and post 3. So if we were trying to do a VSD rectification, then these post 2 and 3 would be separated, but that's not what we're trying to do. We're trying to use this as a gradual pass-through where we can cycle this SCR gate rapidly and gently apply power to the motor. So you'll see that there's a bus bar that connects the positive and negative. So that's what these 2 and 3 are. They're a positive and negative bus. And by putting a bus bar between there and then connecting our motor leads to the other side, here, here, and here, we can maintain our AC output. This confuses some when they're used to like the drive perspective here. So by combining the 2 outputs, we maintain our AC output through the SCR, but we can control how much output comes out of it. So we can gently apply power through these 3 legs to the motor and get that motor to slowly spin up. And then when I say slowly, this is still happening in a matter of seconds, okay? This slowly in relation to this freaking thing just slams closed and it has to haul ass, okay? Slow in relation to that. This is instantaneous. This is slow. That's what I mean as a perspective. This isn't going to take several minutes to accomplish. This is going to take a few seconds at most, if not 1 or 2 seconds. But it's still far less energy and far less stress on the motor than trying to just slam this starter contact closed. And so once this particular style of starter, once the SCRs have gotten to where they can stay fully closed. By fully closed, that means they're just acting as a pass-through device. They're no longer adjusting how much power is going through them. Once they've fully closed and the motor is technically at speed, then we will transition and we can close the starter here to have just the hard mechanical contact, and then we can open these up to allow these to come out of the load circuit. And so you'll have a transition process between the SCR and the mechanical, the electromechanical starter. But again, we gently bring the motor in, which is the whole the soft starter part of the solid state. But the solid state component of this is the SCRs. This is what makes it solid state versus a Y delta starter uses 3 of these starters to accomplish a similar effect, but we do it across, by reconfiguring how the motor windings are configured, from going from a Y configuration to a delta. That's what we're doing with a Y delta starter. Where in this application, we can do that. We can even more gently get the motor online than what a Y delta soft starter could do by applying solid state devices. Now, These cannot stay in the electrical circuit for an extended period of time in this particular application because these SCRs burn a lot of, or they generate a lot of heat by passing that much current through them. They're mounted to a cooling plate. This is a cooling fin, and you can see the thermal paste right here on the bottom of the SCR as a heat sink. So there is some passive cooling happening from the SCR to this plate, but it's very limited, and it's only designed to keep them cool enough to get past startup. Once you get past that, there is not enough thermal mass here and enough cooling system to keep these in the circuit. They will burn up versus a larger centrifugal, kind of an old school style. Let's see if I can pull up a example of that where we've got an active control system, or a cooling system, I mean, to prevent the starter from overheating. Let me find the photo I want to show you. Here we go. This one will work. So this would be a type of, there is no bypass contact here. These are SCRs. They're just much bigger, and they have a steady output, but these are mounted to a cooling plate assembly. Now this would be a liquid cooled style of system where we're flowing a fluid through a heat exchanger, and it's taking the heat away and rejecting it into the condenser water side of the system. So this is how we would cool a larger set of SCRs if these were to stay in the electrical cycle. So these are not meant to cycle over to electromechanical. These can stay in the cycle, and once they fully close, they're just closed. They don't do anything else. And over here, your positive and negative terminals are tied together internal here. So unlike the other style I showed, they were separated into two different terminals because they're just using a standard off-the-shelf SCRs. These are more specific built to this application, to where internally here the positive and negative buses are tied together to rejoin our AC sine wave back together on the output side. And we have our line voltage coming in, but these can stay cool enough. So without getting crazy into the electrical schematics next and diving into that aspect of it, that is what a solid state starter is accomplishing. We're flowing through an SCR to slowly ramp the motor to lower the inrush current so that we save energy and we put less stress on the motor. And then depending on the style, we either transition to an electromechanical, or we transition, or we have enough cooling on the SCRs to lock it in. There are a lot of solid state starting systems still out there that they're still using bypass contacts. That's what the mechanical contact would be considered, as a bypass contact. It is there for after the SCR has gotten the motor up to speed, we transition to the bypass contacts, which will then just carry the line current from there, and we can bring the SCRs out of the circuit. And by doing that, we don't need the cooling system that we need if the SCRs were to stay in the circuit. And so that is one justification for having a bypass contact involved in the first place. And these are the kind of things I go completely in depth into this, and I take a lot more time to really break this down, show you more examples and stuff inside of Chiller Academy. This is in the certification course specifically. I've got a whole section in there on SCRs, how we apply them, and soft starters, and the different applications we have for soft starters, how we cool them. Like everything we've talked about here, I go in to really good detail inside of that course. So if you're needing more of this type of education and stuff, I would recommend moving or checking that out, seeing if that's a good fit for you and the education that you're looking for to help you. With that, we need to wrap this up. I went over on time. I try to cut these off around 1 o'clock-ish my time. We're at 1:09. I really enjoyed the chat today, everybody. Hope you had a good time. I will capture, there's a few questions I know that I did not get to. I will get those questions, and I'll get them saved, and they will be on the list to get covered. We'll be back next week. If you are in Chiller Academy, then you'll see everything post inside of the portal in there. You can keep track of not only this stream, but future streams to come. And yeah, Chiller Academy, everybody in there will get priority sequence in the questions and such as they come in. So just letting you know that I am putting you all at the top of the list if you are in there. And I really appreciate everybody's time. Really appreciate your support. NTT, make the time for your family, for your spouse, for your kids. It's busy season. The time's not going to be there. We have to make the time for them. Um, I really appreciate the support. Next stream I plan to do next week, we're going to talk about the first year anniversary of Chiller Academy and me starting this whole process and journey. And it is your support that's made this possible, made this dream of mine be able to become reality. And so if it wasn't for all of us and what we're doing here, I couldn't be sitting here doing this now, you know. And I, as much as I love the field and I love turning wrenches, I really do. Like, it brings me a lot of joy. Um, I I would much rather sit here and have this conversation with you in the end. And so here we are. And I thank you for that. I thank you for the opportunity to do this. I genuinely, if it wasn't for us doing this together, this whole thing we have here wouldn't be happening. Anyway, y'all have a great week.